I'm going to start the live stream now. Okay. Hi, everyone. Welcome to the Topos Colloquium. Thank you for your patience in waiting. Today, we are very pleased to have Cohen from the Qualcomm AI Research Lab, and he's going to share with us about categorical causality and systems theory. So thank you very much. So please, Taco, whenever you're ready, you can begin.
All right. Thanks for the kind introduction. So indeed, I'm going to talk about categorical causality, a categorical approach to causal inference, and the relation to systems theory. Before I start, because I'm not really an active participant in this community, I will say a few things about myself, and I'll start with a warning. I am not a mathematician. I have had maybe 1 or 2 math courses in my whole academic career. I did, however, learn a lot of math during my PhD and applied that to machine learning. And that's something I like doing very much. Although, as you also hear throughout this talk, I also really care about making the math do something useful. And so a lot of this talk will be about, the theory of causality as it exists, and where I think it's deficient when it comes to applications to AI, and how hopefully some of your brains can be helpful in addressing some of those limitations. So anyway, I had a bachelor's from Utrecht University, a master's in AI, and a PhD in machine learning from University of Amsterdam. I've been involved with a startup as well, and since 2017, I've been at Qualcomm AI Research. Now, my PhD research was focused on geometric deep learning. So we introduced group equivariant convolutional networks, which really kicked off a lot of work in machine learning aimed at incorporating prior knowledge about symmetries of learning problems into neural network architectures. And in this list, you see a number of follow-up works where we generalize these ideas from doing convolutions on groups to dealing with to data that can be thought of as fields on a homogeneous space, or sections of homogeneous vector bundles, if you will, data on spheres and other homogeneous spaces, neural nets equivariant to gauge transformations. And our most recent work in this line is the geometric algebra transformer, which is a transformer-inspired architecture that uses Clifford algebras or geometric algebras to process a wide variety of geometric data. I've also been involved with generative modeling and data compression for a few years, which is a beautiful area because it really combines some deep ideas about probabilistic modeling and its relation to compression, and something very practical, which is making data smaller so that you can send it faster or store it more easily. And recently I've become interested in what I now call interactive learning, which incorporates reinforcement learning, decision making, and also causality, which will be the topic of today's talk. And so now this is where we go to the next slide, and it will take a little bit. Anyway, why study causality as an AI researcher?
I'm sorry, Taco, are you on your next slide? We are seeing the background on the screen. Taco, are you on your next slide? We are seeing the background.
I am seeing a cursor that's waiting, so this is not loading.
Okay.
Quickly.
Okay.
Again,
okay.
I'm sorry about the technical problems here. What I can try is to share my screen on. Okay, now it's switched. Let's see
now it's on the
a
next
little
slide.
Bit more if this works. So why study causality as an AI researcher? So first observation is that AI is progressing very rapidly. And most progress actually happens by scaling very simple methods. So a lot of people believe, and I think the evidence for this is really building up, that intelligence is just something that emerges from prediction, or the flip side of that, compression at scale. In order to predict or to compress data, you need to understand all the structure in the data, and that's all there is to intelligence. So you might ask, are we there yet? Do we have really all the theoretical tools, and from here on, it's just an engineering challenge to get to general intelligence? Now, the causality research community says no, and it will point at the so-called causal hierarchy theorem, which talks about the ladder of causation, which has the level of association or seeing, intervention or doing, and counterfactuals or imagining. And it basically says that if all you have is data at one level, so for example, you only have observational data, you cannot draw from that interventional conclusions. You can't tell what will happen if you intervene on a system by just observing it. And similarly for the second and third run of the ladder. But in practice, and so they will say all sorts of things like deep learning is just curve fitting, and it's forever stuck at run one of the ladder. But then you look at where the actual breakthroughs come from, and people don't seem to be really bothered by impossibility theorems, and deep learning is just marching ahead. And you can look at the methods that have been proposed in the causal inference community, which really have been developed for specific applications in science, in health science, in social science, economics, not really in AI so much. And they're based on things that have a bit of a good old-fashioned AI flavor or statistics flavor: directed acyclic graphs, conditional independence test, identifiability proofs, things you rarely see in modern AI systems. And often they're based on unrealistic assumptions, and they also lack scalability. You can do 5 variables, whereas we want to do 1 million variables. But on the other hand, causality does appear to play an important role in human cognition. So you can ask why, and maybe there's a good reason for that. And finally, what I find most convincing is that you can create examples where confounding, which is a causal problem, leads to catastrophic failure of deep learning methods. And this is a failure that cannot be addressed by just throwing more data or training a larger model. Even in the limit of infinite scale, you can see that the deep learning method will fail. And we'll look at some examples of that in this talk. So that suggests that, yes, causality is worth studying, even if existing methods don't yet scale to AI use cases. Because blindly training on data without considering the data generating process can lead to problems. But we may need to develop new methods that are more compatible with the deep learning methodology, philosophy. They're scalable and validated empirically rather than just based on theoretical ideas. And we may also need to extend the mathematical foundations to make less unrealistic assumptions. And part of what I hope to do today is to inspire maybe some people here to help out with that, with extending these foundations to be more in line with what we actually need for AI. Another question you can ask is, why study category theory as an AI researcher? And I will say again, I'm not much of a category theorist. I'm really a hobbyist in this, and also you will not see any deep results, certainly not by me, but generally today. But still, I find this very useful to learn about it. I've listed a few reasons on this slide. So first of all, I've always felt that learning and doing mathematics is much harder than it should be. And there are psychological reasons for this, which is that the formalisms, the tools, and the notation that we have are often not perfectly adapted to our innate cognitive machinery. And things like string diagrams, for example, can really go a long way at addressing that. And as a sort of a joke, I put this string diagram here, which maybe undermines that point because it looks quite complex. But on the other hand, if you were to try to express something like this in algebraic notation, you would probably have an even harder time understanding what's going on. And there are also structural reasons, which is that it should be possible to navigate the mathematical landscapes, let's say the space of truths, through statements using only few reasoning steps. And categorical proofs are very short and certainly very good at that. And redundant concepts should be abstracted away, so you can learn a lot of math much more quickly. Category theory also provides conceptual clarity, and especially if you look at the causality literature, it's full of confusion and controversy. Mathematics in general has, unlike, let's say, philosophy, the characteristic that it tends to produce consensus on what is true. And we're not really seeing that enough, in my opinion, in the causality literature right now. So that's another reason why I think combining category theory with causality research specifically can be very useful. And generally, it's a useful way to organize knowledge. But I also think we are not there yet. So a lot of work remains to be done. Certainly, in my experience, learning category theory is quite hard. A lot of textbooks assume that the reader knows advanced mathematics already, and also the tools to the proof checkers or the tools for generating string diagram, etc., etc. All of this could be made much better. But as a long-term project, I think this is just incredibly valuable, and it's really the future of mathematics. All right, so the outline of this talk. First, I'll give an introduction to the classical theory of causal modeling, structural causal models. For those who are not familiar with it, we just give a very high-level overview, and then I'll show work by others, not by myself, that streamlines this theory, so to speak, using symmetric monoidal categories, Markov categories, and string diagrams, and so on. Very, very elegant framework. And then I'll talk a little bit about what I mentioned before, which is essentially pointing at a number of what I see as deficiencies of both of those theories when it comes to applications to AI, and also provide a few hints for how I think we might address that. All right, so causal models. Let's dive in. So the main definition that's used is that of the structural causal model, and there are a lot of variations on exactly how this is defined. But here's one typical definition. So structural causal model consists of a directed acyclic graph, as you see here on the right, where each node is associated with a variable yi. Which is called an endogenous variable, one that's produced by the model. And also, typically you associate each of them with some noise variable, or sometimes called exogenous variable ui. You might associate also independent noise distributions with those exogenous variables ui. And maybe you'll include some information about which of those variables are observed versus latent. So in the smoking scenario that you see here, maybe you do or maybe you don't observe the genome. You can still do probabilistic reasoning in either case. And then the key ingredient is that for each endogenous variable, the model includes a causal mechanism, as it's called, which is just a deterministic map between sets from the exogenous variable associated with variable I and the parents, which is a subset of the yi, of the endogenous variables, to this target variable yi. So for example, the variable y4 here, whether or not a certain individual will develop, let's say, lung cancer, is going to be a function of the two parents in the graph, as well as some noise variable ui. And sometimes you also include a set of allowed interventions that you can perform on this model. So we'll talk about interventions more in a second. So it's quite an intuitive framework. Here's there's also a stochastic analog to this. So a causal Bayes net, and this is a bit of a tongue-in-cheek definition, is a Bayesian network with the word causal prepended, by which I mean to say it's just in terms of the information you need to define this, it's exactly the same thing as a Bayesian network. So they're the same kind of mathematical objects. However, both causal Bayes nets and structural causal models, the deterministic analog, are causal, meaning that they are expected to correctly predict the effect of interventions, which we'll define in the next slide. Now, the difference is that in causal Bayes net, unlike an SCM, you have the mechanisms as stochastic maps. And so you don't need strictly any noise variable UI. You just have a mapping or conditional distribution from the pair, of yi given the parents, as you see here. And clearly, if you have a deterministic map like this in an SCM, and you have a distribution on UI, you can push that forward through this deterministic map and obtain such a stochastic map. And the causal Bayes nets cannot be used to reason about counterfactuals where structural causal models can. So the SCM is usually seen as sort of the deeper layer. You can do a little bit more with it than with a causal Bayes nets, and one induces the other. All right, so here's, if you've never seen causality before, this is probably the most important slide to understand. This is about the difference between intervention and conditioning. So intervention is modeled as follows. So the intervention denoted by the symbol do yi equal to little y, or little yi sometimes. What it means is, take this structural causal model and replace the mechanism for yi, let's say the smoking variable, by a constant. So maybe we'll ask someone to stop smoking, and then if we perform our study correctly, we ensure that that's actually what happens. You can say that the influence of genes is now no longer there. This person is sort of forced to not smoke, and that would be an intervention. So the key thing to understand about this is that here we are changing the data generating process compared to just sampling a person from a population and seeing if they smoke, which could be theoretically based on their genetics and a lot of other factors. Now we're sort of forcing it to take a particular value, and so we're changing the process. And so that's something you do before running this process that will eventually lead to potentially bad health outcomes in this example. So it's like, pre-composition, something before. And there are various ways to formalize this. You have these perfect interventions that set a variable to a value. You can also just generally consider modifications of this computation graph. But each intervention yields some new distribution over the variables y. On the other hand, there's conditioning, which is something that you do after collecting data. So you have a data generating process, you get some distribution over your variables, and then you can say, well, I filter out all the people who smoke, and I just keep the ones who don't smoke. And then I look at the distribution over the other variables. And that's what we call conditioning. That's, of course, very well known by anyone who's done statistics, whereas this notion of intervention is something that's a causal notion. Now, one very important thing to realize is that the intervention on one mechanism leaves invariant all the other mechanisms. So if you intervene on smoking, this arrow here goes away, everything else remains the same. And that's really the key to what we mean by those mechanisms being causal, whereas others might be spurious associations. So here you see an example. If you measure two variables, the chocolate consumption per capita in a country and the number of Nobel Prizes in a country, you can find a correlation. You can predict Nobel Prizes from chocolate consumptions, right? And that correlation is just there. If you collect more data, you'll find it's more robust. It doesn't go away with more data, but it might go away when you intervene, because you might think, well, let's have everybody consume more chocolate and we'll get more Nobel Prizes. But actually that intervention now changes the data generating process. And it turns out this relation between variables is not robust. The way we think about it is that there must be some confound or some variable here. Let's say the the wealth in a country or something that allows people to consume more chocolate and also provides the conditions that lead to Nobel Prizes. If we were to intervene on that, maybe we would have success at increasing Nobel Prizes, but intervening on chocolate consumption will not. So this invariance of mechanisms is a key concept. Here's an example from AI, from a paper that we published recently, where this problem, where this notion of confounding leads to problems. So there's this paradigm of imitation learning, which is a way of learning behaviors or policies. It's very appealing because the idea is to just collect behaviors, so trajectories of states and actions in a long sequence from some expert. So maybe a human driver, for example. You collect all the video frames and the steering commands. You have now a big data set, and now all you need to do to learn to drive is just learn to, let's say, predict the action that the expert would take in each situation. But what can happen is that perhaps the expert has access to some privileged information, like, let's say, maybe they saw the weather report and they know the road is slippery and they decide to drive slowly, or maybe they saw that it's not slippery and they decide to drive faster. But the imitator may not have access to that privileged information. And that's denoted by the variable theta here in this graph. And so the relation between the expert data generating process in this graph and the graph for the imitator is that, well, they're related by an intervention where the action of the imitator cannot be informed by this latent variable here, this theta. This is a confounder. It's a common cause that affects the action as well as the next state, because on a slippery road, the next state will be different from a non-slippery road. And yeah, this can lead to problems because what ends up happening if you just fit a model to predict the next, to predict the action given the past states and actions, is that the imitator will start to take its own actions as evidence for this latent variable. So it will think, I've been driving fast recently, and in the data set, there was only fast driving when it was safe given the road conditions. Therefore, it's fine to keep driving fast in the future, but clearly that's a fallacy. And so you have to take this into account if you want your imitation learning to actually work. And we developed a method to do this. We have a demo here, but in the interest of time, I will skip over this. You can have a look at the paper if you're curious. Deconfounded imitation learning. This problem can also occur in language modeling, of course, very hot topic right now, where you're predicting the next token given previous tokens. But again, there's a latent variable. That's let's say, the author or the intent of the author when he was writing these tokens. And this can lead to problems when the AI starts writing something, then maybe they state some fact which was just hallucinated. And because authors who wrote stuff on the internet, when they were stating a fact, they actually believed it, and they will be likely to defend that position. The LLM will then continue to defend this fact even when you state that it's false. However, existing training procedures probably already address this. So that goes back to my point, like, do we actually need tools from the causality literature? Maybe not in this case. Because the existing training procedure consists of, training a conditional distribution. So that's still problematic from a causal perspective. But that's then followed by a fine-tuning step on so-called instruction following data, where maybe the model learns to say, oh, I'm sorry, I made a mistake. You're right. And then there's an RL training stage where you learn from human feedback, where they give a thumbs up or thumbs down to the output from the model, and this does not suffer from confounding. So it's still potentially interesting to think about. Okay, I've already mentioned the causal hierarchy theorem, so I will not dwell too much on it. But one last important concept from the causality, the classical theory of causality, is the so-called potential outcome function. So a structural causal model induces so-called potential outcome mapping, which you get by just composing all the mechanisms in the model in an order compatible with the DAG. And in the end, you just get a single mapping that takes all the exogenous variables and all the interventions that you performed. So it could be no intervention or an intervention on one variable or multiple variables. And based on that, it deterministically produces an outcome Y. And you can do the same thing for a stochastic model, CBN, where now you just map the intervention to a distribution over the outcome variables. And it turns out that this potential outcome map is actually equivalent to the SCM. It gives exactly the same predictions as the SCM. And yeah, as I said, the potential outcome map can be derived from the SCM, but the SCM can also be derived from the potential outcome map, and that those processes are inverses of each other. And indeed, this potential outcome map can be taken as the starting point for a theory of causality. And that's actually one that's quite popular in the social and biomedical sciences. It's not the case that all mappings of this signature correspond to SCMs. And I'll get into that a bit more later, because that is where a lot of these unrealistic assumptions start to enter in the picture. But yeah, the interpretation that I assign to this is that from this potential outcome perspective, causal inference is really about generalizing from observations from F of star indicating no intervention, to the value of this function F at other evaluated other interventions. It's like doing image classification, but you're only observing one image, and there's some distribution over the labels, let's say. So that makes it clear that first of all, it's actually just from that perspective, it's just statistical learning still, just a very extreme and weird case. And also makes it clear that if you really want to do this, you're going to need tons of assumptions, tons of prior knowledge to have any chance of generalizing to these other interventions that you never saw. Okay, so there are a few causal learning problems. There's causal discovery, where you're trying to infer the graph using conditional independencies in your data. There's causal inference, where you are given a causal graph or some knowledge about it, and you're trying to infer the causal, the quantitative mechanisms, actual functions or conditional distributions, and causal effects from data. And then a bit more sort of new from the AI community is this idea of causal representation learning, where you acknowledge that the variables that are incorporated in a causal model are typically very abstract, high-level variables, whereas an agent, let's say a human or a robot, will ultimately only observe low-level sensory measurements like pixels. And the job here is to learn the variables in the causal model as well as the causal model itself. And the thing I added to this, which hasn't really been picked up yet, but I think will be very important, is causal intervention learning, which is about learning to intervene. So, for example, if you have a robot, it's useful for it to know that turning the light switch causes the light to go on. It's not just a correlation between the state of the switch and the light. It's actually, if you flick the switch, then the light will go on. That relation is robust to this intervention, but it should also actually know how to do that action, which is a rather complicated thing to learn. And that knowledge should somehow be integrated with its world model, its knowledge about this causal relation. Right, so there's a lot of work on causal representation learning, but I will not talk too much about it in the interest of time. So then the categorical theory of causal models. As you saw, the definition of an SCM is quite hairy. It's not doesn't have a categorical flavor. So people have been working to streamline this definition. And I'm going to focus in particular on, all of these works here in this list have contributed to this, but the ones that I sort of would recommend most, because they assimilate a lot of prior works and just explain things very nicely, is this work Causal Inference by String Diagram Surgery, and very recent paper Causal Models in String Diagrams, as well as not listed here, but work on Markov Categories by Fritz. So I'll go over this relatively quickly. So the basic idea underlying these works is to have a clean separation of syntax and semantics, something that is already implicitly there in the classical theory, where you have a graph that gives you sort of qualitative information about what might cause what, and more importantly, what certainly doesn't cause what. So the absence of an arrow is that's where the information is. And then there's a quantitative part. There's the functions or conditional distributions that we associate with these edges. In the categorical approach, we're going to formalize this by having so-called syntax category that takes the role of the graph. And then there's a semantics category. It could be a category of sets and functions, or the category of stochastic maps, or any other so-called Markov category. And there's going to be a functor that assigns to each node and each edge, essentially, some object or morphism in this category. I think I'm preaching to the char here, but this is an instance of functorial semantics. And it, just as a personal note, I have already encountered this earlier in my career when I was working on group theory, where you have a group and you have a group representation, which you can think of. So the group you can think of as a one object category, with every morphism being an isomorphism. The group representation then can be seen as a functor to the category of vector spaces. And equivariant maps, which are the things we are learning in geometric deep learning, those are the natural transformations are equivariant maps. And we want to apply this approach to causal theories and models. So the key notion here is that of a CD category or a Markov category, very closely related concept. So a Markov category, C, is a symmetric monoidal category in which every object is equipped with a, if you want to intimidate someone, you say commutative comonoid structure given by this and this. If you want to just give the intuition, you say, well, you can copy things. So if you have an object X, you can create two copies of it. And you can delete things. So if you have an object X, you can map it to the monoidal unit. And they satisfy all sorts of very intuitive properties that you would expect for copying and deleting, such as if you copy something, you read these string diagrams from bottom to top. If you copy something and then delete one, that's the same as the identity doing nothing or deleting the other one. It's commutative. In that if you swap the outputs of copying, that's the same as not swapping them, and so forth. This last property here says that if I have any process, you can think of that as a stochastic map, let's say, and I delete the output, that's the same as just deleting the input. That is a property only true in Markov categories, whereas in CD categories, this doesn't need to hold. Anyway, the upshot here is that this gives you a very nice diagrammatic language that manages to capture a lot of probabilistic reasoning and statistics. And I find it, I find this quite intuitive. So whereas in classical statistics, if you learn about independence, you have to learn it in some algebraic way, where you're talking about the distribution being a product of two distributions, and then you have to think about, okay, why does that embody the idea of independence? And here you just have a nice simple picture. It says that if I have some stochastic map F that takes one input and produces two outputs, if it is the same as copying the input and then mapping both copies through some other stochastic maps G and H, if there exists such G and H, then we say that the outputs are conditionally independent given the input. Super simple, intuitive statement. So again, this is why I think once we actually explain this at a really elementary level, this can actually make learning probability easier for people. Well, I have an example of a Markov category, but I'm not going to go and read all of this. But the category of stochastic maps has as objects finite sets, the things over which you have probability distributions. And then as morphisms, it has stochastic maps or, if you will, conditional distributions. And that's an example of a Markov category. Now, the idea of categorical causal models, as I noted before, is that we're going to have some theory category. So let's say we have a DAG. We can build from that the so-called free CDU category on a DAG. In this work by Jacobs et al., they don't work with CD categories, but CDU, meaning there's also something that represents a uniform distribution on a variable. It's a minor difference. But they construct a free CDU category on a DAG, meaning for each node you get an object. For each mechanism or for each node, there's also a morphism that produces that. For that object essentially, and then you can also take monoidal products, and you get a free object like this. Very sketchy description. You can look at the paper for details. In that category, there's sort of one main morphism denoted by, or which you can represent as a string diagram, which represents the causal model. So the smoking example I showed before looks like this as a string diagram. There's some process that with no inputs producing let's say the genetics of the person. The output of that is copied and fed into the process that decides whether the person smokes. This is copied and output. You can measure whether someone smokes, and whether they smoke also is fed into the process that determines whether there's tar deposits in the lungs and so on. Just a different way of encoding the same graph, but now it has a categorical interpretation. And so you can define a functor, which now assigns to each node an object, and to each morphism a morphism in the category, let's say, of stochastic maps. And an intervention now can be described as a endofunctor on the syntax category, on the causal theory, which basically replaces the generators, the mechanisms for each variable, for the variable that you're intervening on, by another map which just deletes all the input and then samples the variable from a uniform distribution. That's the type of intervention you're considering here. And you can describe this as an endofunctor. And you compose it with your model, and now you get a intervened model. So that's very neat. And you can now do identification of causal effects in a purely diagrammatic way. And the idea is to use something called a COM factorization. So COM is a morphism with, let's say in this case, 2 inputs, 2 outputs, that has the property that if you delete the second output, you might as well just delete the second input, because to produce the first output, you don't need the second input. So that already has a causalish feel to it. It's also called non-signaling. It means that A2 doesn't affect B1, so to speak. And you can introduce some nice notation. I will not describe this in great detail. But basically, the key result is that if you have any distribution on, let's say, smoking, tar, and cancer, in this example, then you can uniquely factorize it into a 2-comb and some other morphism. And because we know that this distribution here is composed of the mechanisms that we are drawn here on the right, you can identify what this 2-comb must be. So you can fit that from data and fit this conditional from data. And then what you can do is you can just insert a cut here. And using purely diagrammatic reasoning, you then show that it's actually equal to this diagram here on the right, which, lo and behold, is the intervened model, I should say. And so given two things, G and F, that you can actually determine from observational data, you now can compose them in a funny way with a cut inserted, and you get the interventional distribution. And so this will tell you whether indeed, if you stop smoking, you will have less cancer, or whether the correlation between smoking and cancer was actually caused by what the tobacco company would love to believe, that genetics predisposes someone to cancer and also to smoking. And of course, the data does not bear out that, or not support that theory, but here you have a way to actually show that. So beautiful framework. I highly recommend reading it. Now about the future and what we actually need for AI. So this necessarily is going to be a bit more sketchy, because I've been thinking about this for quite a while, but I haven't had time to actually to converge on something really publishable. But I'll share my ideas, and I hope someone is interested enough to pick this up. So as I mentioned before, the theory of causal models has been developed for use by human scientists. So there's always a scientist that chooses the variables, that chooses that now I want to study the tar in the lungs. That's probably relevant, and the disease outcome and so on. And they also know how to measure those things operationally. That's not always easy, right? There's a whole complicated, there's a lot of intelligence in just collecting that data. It's also the scientist that performs the intervention, that assigns the treatment to the patient, or flicks the light switch, or whatever example you want to think about. And they use common sense to avoid all sorts of issues that are not really, for which are only, natural language guidelines, not mathematical results. And the models are also always limited in domain. It's a model about lung cancer or heart disease, or about how minimum wage affects employment or something like this. What we need in AI is, we want to build autonomous agents that can learn representations from low-level sensory inputs, that learn skills, how to intervene, how to change things. That we cannot rely on pre-existing knowledge, right? Building in common sense knowledge about everything in the world is not going to work. We're much more likely to have, let's say, a large language model that read the whole internet and knows a lot of things about a lot of things. And we want these models to be general. So how are we going to get there? Well, I'll go through a number of observations that I think are salient and that should inform the design of more general frameworks. So the first key observation, I think, is that causal models are always abstractions. They are simplified models to facilitate simple reasoning. The causal variables that you find in typical causal models are far removed from sensory inputs and micro variables that describe a system. Also, this notion of a direct cause is never really fundamental. If you say the cholesterol causes heart disease, we can draw it with you can say it in a simple sentence, draw it with a simple diagram, but that arrow here is hiding a lot of, a very complicated process. I can introduce many variables and arrows here that, tell this story in a more detailed way. So there's some important implications of that, I think, which is that we can always represent a system at different levels of abstractions. And to me, that means that aiming for identifiability of the causal variables, as people do right now in causal representation learning, is probably the wrong approach. So instead of finding the so-called true causal variables and mechanisms, which is a theoretical fiction, just try to find some set of task-relevant variables, as people do in machine learning these days, plus some mechanisms that are causal, or meaning invariant, or for which at least their domain of validity. You know which actions will break this relation between variables and which will not. Okay, so one related problem is this notion of ambiguous interventions, which has been identified but not really resolved, was already identified in 2004. which is that the effect of an intervention actually depends on how it's implemented. So I might have this model and I might believe it, that cholesterol, total cholesterol, causally affects heart disease. But what does it actually mean, right? I'm going to perform an intervention, and what the framework allows me to do is to say I set total cholesterol to a certain value. But what I'm really doing is I'm assigning someone a diet or a medication or an exercise program, and I know that will influence the cholesterol level. But depending on what exactly I do, it may have a different effect on LDL and HDL cholesterol. And those have different effects on heart disease. And so how exactly you implement the intervention, that's very relevant. So I think it's actually problematic to identify the value of a variable like total cholesterol with the intervention that you perform. That's something we probably shouldn't build into the framework from the bottom. Yeah, so we need some a priori definition of intervention that's not tied to the choice of variables. There's some other issues with this notion of intervention and mechanism as it's described in SCMs. So first of all, it's not always the case that all joint interventions are jointly possible, even in principle. So for example, if you think about an ideal gas, you can perform interventions to set the pressure. You can perform interventions to set the volume, the temperature, right? There are concrete things you can do, like turning on the heater or whatever. But the ideal gas law tells you cannot simultaneously intervene on all three of those variables and set them to arbitrary values, because certain things are impossible. If you set two of these variables, the third one is determined. Another thing is that not all actions that we can perform they don't all behave as interventions in SCMs. So an intervention in SCM, they always commute. If I intervene on one variable and then on another variable, I get the same intervened model as if I do those interventions in the other order. But clearly that's not true for all actions that someone could do. And they also annihilate. If you intervene on the same variable twice, I set the light switch to on and then I set it to off. That's the same as just setting it to off right away. That's baked into the framework, and probably it shouldn't be, because there are a lot of actions that don't satisfy those assumptions. So I think properties such as these should be encodable, but not assumed by default. And we want to have some algebraic structure, like a monoid expressing the commutativity or annihilation properties of your actions that practitioner can use, but doesn't have to use. And now I'm trying to move to the next slide. Here we go. So another observation is that causal variations are local. So here's an example. Let's look at this situation, the sort of canonical example of causality of one domino causing another to fall. And we have a model of it here, which records the fallen or upright state of each domino and the causal relations between them. And it's a reasonable model. I think everybody would agree. But what if, does it even mean for the domino to be upright or fallen? The meaning of this variable is, only prescribed in some subset of the state space, where I change the number of dominoes. I can do any number of things that take me outside of the domain of validity of this model. So, we can also include those, but whatever you do, it's always going to be somehow limited in scope. And so the analogy that I like is the idea of charts on a manifold, right? You have a global structure, the manifold, and you have some local variables on it. And if you choose them well, then everything might work very nicely, right? You might get a nice sparse causal structure, for example, or in the case of manifolds, you might get your metric is diagonal or whatever. But they only describe a piece of the whole, a partial sketch of the elephant, if you will. And you want to think about how those partial models overlap and how you can go from one to the other. And only in that way can you sort of piece together the whole thing and express all of your world knowledge in one coherent way. Now here's a interesting result. I don't have much time to go into detail, but There is a theorem already from the 90s due to Pearl and Galas and Halpern that characterizes the potential outcome maps that come from a structural causal model. And it turns out they satisfy 3 axioms, and any mapping satisfying those axioms comes from a structural causal model. And this is hailed as some very beautiful result, that it's the axiomatic characterization of causal counterfactuals, they call it. But in fact, it highlights the limitations of this SCM framework in that it cannot express any mapping, whereas nature might throw something totally different at us that we need to be able to describe as well. So we need something more general. Yeah, on this slide, I have a few questions about or mathematical questions that I encourage people to look at. Then I think what is probably a suitable framework to start addressing these issues is the framework of open dynamical systems, which very briefly describes a system in terms of some object X, the set of states. Shouldn't say set in this crowd, but object, and some actions A, and there's an update map that says if I perform this action, what state will I end up in? Could be a stochastic map, could be continuous time, discrete time, lots of possibilities in this framework. It's a beautiful book by, partially written, but beautiful by David Jazz Myers. The other part of the system is the expose map that tells you what you can actually observe from the state. And this is a framework that's already used in AI, where it's called the POMDP, partially observed Markov decision process. And it's also an instance of a lens, which is one of the favorite toys in applied category theory, I think. So there's a lot is known about this kind of thing. And so why do we like this? Well, here interventions or actions are defined without reference to some outcome variables. You just have some A, and if you put it into the update map, you get a transformation of the state, and that's the intervention. It can encode algebraic structure, like you could say the update map is a monoid action. It comes with all sorts of well-defined composition operations and wiring of systems together. You can do all sorts of very interesting things with it. Model abstraction is well-defined. And it relates to causality in the following way, because it turns out you can derive from a system a potential outcome mapping. And as we saw, we can also do that from an SCM. And so now you can ask an interesting mathematical question, which is, if I have a potential outcome mapping that satisfies the axioms, meaning it came from an SCM, what does that tell me about my system? And I have some partial answers to this, but nothing very concrete. So I think it's an interesting question to think about. Now, when it comes to describing local causal-ish behaviors, I would propose the following strategy. So this is an idea from categorical systems theory, and also described in this very nice book by Lauver called Conceptual Mathematics, where you have a system here shown the internal picture of a dynamical system with no inputs, no outputs for simplicity. And if you want to describe something like a trajectory or a fixed point or a limit cycle, you can do that by having sort of a simple model that captures the essence of it, like the essential 3 cycle is this little model here. And you just map it into the object, the system of interest, using typically a mono map, injective map, and in that way you point at the 3 cycle. Now this can be applied to causal models as follows. So let's say you have a system. It's not going to represent the essence of a limit cycle, but the essence of an invariant mechanism. It has a state space X and update and expose maps. And let's assume that the outcomes consist of 2 variables, which we think of as the parents and the target causal variable associated with the mechanism. We can say that this system has a global invariant mechanism. If this is true, if producing the outcome and then only looking at the second variable, the target variable, is equal to producing an outcome only looking at the first variable, the parent variable, and then mapping that through some mechanism F. If that is true for the system, we say it has a global invariant mechanism, because whatever actions I do, you can always determine one variable from another via this mechanism. Now, if you map such a system into a larger system, what you're doing is you're pointing at a subset of actions and a subset of the state space or sub-object in a more general context, where this mechanism is valid. And I haven't completed this, but I suppose that if you have a lot of these causal behaviors and they relate to each other in particularly nice way, you can show that your system or the potential outcome map derived from it is equivalent to an SCM. But you now have a much richer framework where you can also express deviations from that. Now, I'm at the end of my talk. So as I said, I haven't completed this work. I'm really presenting this in the hope that someone with more time and more mathematical skills than I have will be interested in picking this up. But some of my thoughts I have written down, so you can have a look at that. Yeah, feel free to contact me if you have any questions or would like to work on this. And that's it. And I'm happy to take questions if there's still time.
Right. Thank you very much, Taco. And I think we have time for one or two short questions for the live stream. And then what I'm going to do is after the ending of the live stream, if we have more questions from the audience, we could say, Taco, if you're free, you can stay on and we can ask those questions there. So let us first thanks Taco for the talk. So okay, for all the people in the live stream in the Zoom room, please feel free to raise your hand or unmute yourself, or you can ask the question in the chat, and I will try to ask your question for you. So I see that we have one raised hand from Nelson. Nelson, would you like to?
Hi. Yeah. This was a really cool talk. I was just one small thing. You mentioned about how like you want to think about causal models locally, and you drew that analogy to charts on manifolds. And I think my first reaction was, oh, you're going to talk about sheaves, right? And then you didn't talk about sheaves. So I'm curious, right? Like how, like, could you apply sheaves to capture this sort of like local nature of like causality models?
Yeah. So I didn't talk about it because I don't want to waffle, and I don't have something very how shall I say, very clear and detailed. But I did indeed try to hint at various things that so I'm happy that this concept was triggered in your brain. And I think that is a perfectly reasonable strategy to try to formalize these intuitive ideas. And that's about as much as I can say about that at the moment. But yes,
Totally valid. Yeah.
That's yeah.
Thank you.
Okay. I see that we have a question from Valeria. Valeria, would you like to unmute yourself?
Thank you. Hi, Taco. That was really very cool. Liked it a lot. Question is about the CDU categories, because I thought the U bit was the only bit that had anything to do with probability, because, copy and discard are things that I personally mostly associate with logic, where you kind of duplicate or discard premises. So I was wondering whether you kind of have any special reasons for not paying attention to the U, the uniform distributions, right? I mean, I'm trying to remember what you said. I don't know much about it.
Yes, that's an excellent point. And I think that this points at one of the aspects of the theory that's perhaps still a little bit in flux. I listed this on a slide, although I didn't mention it, but one downside of these CDU categories is that they kind of mix the syntax and the semantics here, because for example, if you wanted to express the idea of a intervention setting a certain variable to a certain value, right? What you actually have in the standard SCM framework. Right. Well, you have to talk about the value. So now you have to talk about the elements of the set, which lives in the the semantics category, not the syntax category. Uniform is kind of one thing that maybe you can squeeze into your syntax category. But yeah, anyway, this is still a little bit fuzzy. You can include a lot of things in your syntax category or uniform distributions. You can also incorporate so-called sharp states, which is basically just values, or let's say delta peaks on a particular value. And yeah, I don't know if that answers your question, but
yeah, no, I think it does. I think it does. As you say, it is still a little bit in flux, right? It is still this
really just a pragmatic choice in that paper to focus on interventions where you sort of randomly resample a variable. Like, let's say you wanted to randomly assign patients to a treatment group of either smoking or not smoking, randomized controlled trial. Of course, ethically you can't do that, but what they showed there is actually you can still get the well, you can figure out what would have happened just based on observational data and assumptions. And for that example, they needed uniforms, so that's why they put the U in there. But you can do other things as well.
Okay, thank you very much.
Hey, thank you, Valeria and Paco. I think we have time for only one more question, and I see that we have a question from the Topos Institute seminar room. So, Evan, maybe can unmute and ask the question.
Hi, Xiaowei. Hi, Taco. This is Brendan Fong. I just want to say thanks for the talk. Dana Scott has a question.
I didn't know how much time we have. I could write him an email.
No, go ahead.
Okay. Here's an impression I have about machine learning, but understand that I come from the side of formal logic and math, and I don't know how to use machine learning technically. But listening to many talks about it, I have the feeling that in mathematics, we don't have the right kind of data in order to effectively do machine learning. For example, with computer-assisted theorem proving, we have very big databases for various popular systems where a user can look at successful proofs and then by analogy figure out how to do new proofs. But that doesn't mean that we can teach an AI system how to reason by analogy to understand developments of proofs. Or look on the other side of the published mathematical literature, which is vast, of course. But when mathematicians read a paper, they're mixing natural language with formal language. Often when they come to a formula, they don't even repeat the formula in detail. They just give you an impression of the formula, but it's enough for understanding so that people can get something out of what's in. And again, it's very hard to teach an AI system how to read on that higher level rather than getting bogged down into details. And now you gave the example of computer algebra. I'm sure there's very good databases of successful use of computer algebras that you could apply with machine learning. But again, that's rather specialized. What about the string diagrams? Do you have databases in string diagrams so that a system could actually learn how to put string diagrams together? I'm sort of skeptical on that. In other words, that we don't have enough mathematical data in order to help machine learning. Am I wrong?
Yes, that's a very interesting topic. It's actually one of my current interests to think about this and automated theorem proving and similar topics like code generation. I think that in terms of really formal proofs, there is indeed a scarcity of data. I think there's plenty of data of this sort that mathematicians actually produce, like the LaTeX files that you'll find on the archive. And actually, large language models can learn very well from the latter kind of data because it's present in such large volumes, and they are starting to understand quite a lot of it in a way that's quite similar to how mathematicians understand things, I think. And then they understand even the analogies and the things that are left implicit. We're not quite there yet, for sure, and I don't know if we'll get there using purely that approach. But one thing that I'm quite excited about is to start using reinforcement learning, where let's say the theorem prover will itself just start to explore reasoning steps within some formal system and discover strategies for proving things on its own. And in that case, the data is generated by the exploration process itself, and so you don't need human generated data. I think this is an area that that's just very, very exciting, both for what it can do for mathematicians and as a research problem for machine learning people.
Okay, I think I'm going to end the live stream on YouTube soon. First, let us thank Taco again for the amazing talk.
Thanks.
And I'm going to end the live stream now, but we can stay on in the Zoom room if there are more questions. Okay.